I'm sharing my screen. We'll start with the next topic, that is multiplexers. What are these multiplexers? We'll see. MUX. Multiplexers. So multiplexers, in simple word, MUX we'll call. It consists of 2 power n inputs and n selection lines, and single output. Single output. Okay. So at a time, so from the 2 power n inputs, depending on the selection line, only one input is connected to the output. One input is connected to the output. Okay. So we can implement by using this MUX, we can implement the Boolean functions. We can implement the Boolean functions. Okay. And we can implement the combinational circuits also. We can implement the combinational circuits. Okay. So other name for MUX is data selector. Data selector. Data selector, or we can call as a universal circuit. Universal circuit. Okay. So other name for MUX is a data selector or universal circuit. Okay. So if you see the basic MUX, so this is MUX. This is MUX. Let us take this is 2 power n cross 1 MUX. 2 power n cross 1 MUX. Okay. So 2 power n cross 1 MUX. So you have 2 power n inputs, 2 power n inputs, and one output source. Okay. One output source. So this is output. Okay. And n selection lines. You have n selection lines. Okay. Okay. This is a basic structure for the MUX. Did you understood? Shall I move forward? Okay. Next. One second. Yeah. Next. First, we'll start with 2 cross 1 MUX. So what is this 2 cross 1 MUX? So 2 cross 1 MUX. So it have two inputs and one selection line and one output. One output. Okay. So if you see the block diagram, so this is 2 cross 1 MUX. Two inputs are there, one output. Let us take the inputs are I0 and I1, and enable pin is also there. Okay, enable pin is it's acting like means it's like acting like a switch. Okay, enable pin. So enable pin and selection line and output y. Okay, output y. So if you see the truth table for this 2 cross 1 MUX, so here you have enable pin, selection line, and output y. So when enable pin equal to 0, whatever may be the selection line, you are getting the output equal to 0. Okay. So, and when enable equal to 1 only, then the MUX is set to be in, we can say that it is functional mode. It is set to be in functional mode. Okay. Functional mode. When it is 0, which is connected means when S equal to 0, I0 is connected to the output. I0 is connected to the output. Okay. When S equal to 1, which is connected means I1 is connected. When S equal to 1, I1 is connected. Okay. So from this you can get the Shannon's equation. Shannon's equation. So what is the Shannon's equation? That is y equal to S equal to 0. That is S bar I naught plus S I1. S I1. This is the Shannon's equation. So from this I can draw the logic diagram. So let us take So this is I naught, okay, and here you take yes, yes, and it is giving through the inverter, and one more enable pin, okay, enable pin is there, enable pin is there. This is enable, so this is given to mm, which gate means AND gate. So here you are getting enable, enable. So here you can write this is enable. Okay, enable is also there. Okay, enable S bar I naught. Again, let us take one more input that is I1. Enable, enable. Yes, so yes, enable and I1. It is connected with AND gate. Enable yes, I1. These both are connected with OR gate. So here you are getting that y equal to enable S bar I naught plus enable S I1. S I1. This is 2 cross 1 marks. Is it fine? Okay. Next, if you see the 4 cross 1 marks, 4 cross 1 marks. So it have how many inputs? 4 inputs and 2 selection lines and one output. One output. Okay. So if you see the block diagram, 4 inputs are there. Let us take the 4 inputs, 2 selection line. Let us take the inputs are I naught, I1, I2, and I3. Selection line S naught and S1, and this is 4 cross 1 mux, and output is Y. Output is Y. Okay. So if we see the truth table, so you have enable 2 selection lines S1 and S0 and output Y. Okay. And here when enable equal to 0, whatever may be the selection line, the output is what? 0. Okay. And when enable equal to 1, when selection lines are 0, 0, which is connected to the output at a time, one input is connected to the I naught. So this is I naught. And when it is 1, 0, 1, I1, 1, 1, 0, I2, and 1, 1, 1, I3, I3. Okay. So here, so you can draw the logic circuit. So let us take the 4 inputs. What are the 4 inputs? I naught, and next I1 and I2 and I3, and selection S1 is there, no? So S1. So this is S1. S1 connected with an inverter S1 bar, and S0 connected with an inverter S0 bar. Okay, and enable is also, so enable is there, but here I'm not indicating. So here I naught S1 bar S0 bar connected with an AND gate. Okay, and I1 0 1 0 1 means what? S1 is 0 and S0 is 1 connected with an AND gate, and I2 where is I2 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 S1 S1 S0 bar connected with the AND gate, and I3 S1 S1 S0 S1 S0 connected with an AND gate. These all are connected with an OR gate. This is OR gate. Yeah. Why? Because here, so y equal to, if you see here, Shannon's equation. Shannon's equation. When it is 0, 0, 0, 0 means what? S1 bar, S naught bar, I naught plus S1 bar, S naught into I1 plus S1, S naught bar into I2 plus S1, S naught and I3. So bar means I am getting through the inverter. This is nothing but S1 bar and S. Yeah, equation I'm doing. Yeah, Shannon's equation. Okay. This is 4 cross 1 marks. Shall I move forward? Okay. Yeah. Applications of MUX. Where you will use this MUX? Applications of MUX. You see the applications of MUX. Let us take multiple sources are there. Multiple sources. Multiple sources means you have like MP3 player. Okay, MP3 player and laptop sound card. Okay, and digital satellite, and next digital cable TV. Okay, so you are getting multiple sources. Okay, so here you have a selector. So here I can use 4 cross 1 mux. Okay, so this is 4 cross 1 mux. So these inputs are given to this 4 cross 1 mux. Okay, and you have two selection lines. Let us take the selection lines are B and A. So select the source. Select the source. Suppose if it is 0, 0, which so this is connected to single destination. Single destination. Okay. So output is what? The output is my sound. No? So it is given to sound box. Okay. So this is surround sound system. Surround sound system. Okay. So select source when it is 0, 0. So MP3 is connected. When it is 0, 1, laptop is connected. And when it is 1, 0, satellite is connected. And when it is 1, 1, cable TV is connected. Like this. These are the applications of MUX. Did you understand? Okay. Next, we'll see the how to implement higher order MUX by lower order MUX. Okay. How to implementation of higher order MUX by lower order MUX. Higher order MUX. Higher order MUX by using lower order MUX. Okay. So here what you need to do. So step one. Step one. Calculate the number of MUXes required. Calculate the number of muxes required by dividing higher order mux with lower order mux. Okay, and step two, continue till you get one. Continue till you get one. Okay. Step three, add all number of muxes and connect. Add all number of muxes and connect. Okay, these are the steps. Okay, suppose example, if you take you want to realize means if you want to implement 4 cross 1 mux using 2 cross 1 mux. First what you need to do, higher order mux 4 divided by 2. So what is the quotient 2? So this comes in the first stage. Okay. Again 2 by 2, 1. So this comes in the second stage. So what are the total muxes required? 2 plus 1, 3 mux. Yeah, we have to add the quotient. This one and this one. 2 plus 1, 3 muxes. So first stage 2 muxes are there. Okay. First stage 2 muxes are there. Uh, I naught, I1, and here I2, I3. So this is 2 cross 1 mux, first stage. Hmm. So one more 2 cross 1 mux, 2 cross 1 mux, second stage, and this is given to output. Okay. Common selection line is there. So this is S naught and this is S1. Okay. Enable is optional. It will be there or not. That is optional only. But mainly inputs, you need to indicate the inputs and selection lines. Okay. Suppose 8 cross 1 mux using 2 cross 1 mux. How many are required? Let's try this. Ah, 2 is to 1. Only using 2 is to 1. Before I told you the steps, no? These steps you need to follow. Ah, 4 to 1. Yeah. So 8 by 2. So 4. This is first stage. 4 by 2, 2. This is second stage. And 2 by 2, 1. This is third stage. So here, so in the first stage, 4 cross and mux. 4 cross and mux. And so this is I naught, I1, I2, I3, I4, I5, I6, I7. Okay. And these are given to, this is first stage. And these are given to one more 2 cross 1 mux. And these are given to one more 2 cross 1 mux. So common selection line for this one. This is S naught, common selection line. And here also common selection line. This is S1. Okay. And this is given to one more 2 cross 1 mux. And this is the output Y. So this is selection line H2. So this is first mux, second mux, third mux, fourth, fifth, sixth, and seventh. So in general, suppose 2 power n cross 1 mux is there. How many muxes are required to implement suppose 2 power n cross 1 mux is there. How many 2 cross 1 muxes are required? Hmm. Yeah, 2 power n minus 1. 2 power n minus. Initially we got 3, no? 4 cross 1 mux means 3. Here you got 7. Okay, 7. So that means 2 per. This is the general formula. Suppose 64 cross 1 mux is there. You need to implement by using 2 cross 1 mux. So 64 minus 1. How many? 63 are required. Like that you need to implement. Okay. And coming to 8 cross 1 mux using 4 cross 1 mux. 8 by 4, 2. 2 by 4, how much? And then how to implement? But point 0.5 you got, no? Anyway, first stage you have 2 marks, 4 is to 1 marks. So I naught, I1, I2, I3. Okay. I naught, I1, I2, and I3. And this is I4, I5, I6, and I7. Two selection lines are there, S0 and S1. Okay. And one more enable pin is there. Enable pin. This is the enable pin. Enable pin is given through this one more selection line enable pin. This is S2. Okay. And S0 and S1 are common selection lines. And this is given to OR gate. This is given to OR gate. Okay. OR gate. This is the output. Output OR, you can say. Yeah, OR gate. Yeah, OR gate. Suppose if you take the selection line S2, S1, and S0. Okay. And let us take the output Y. Okay. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. No? So if you divide, so here I naught, I1, I2, I3, I4, I5, I6, and I7. No? See here, S2. When S2 equal to 0, S2 equal to 0, this becomes what? 1, no? This becomes 0 means what? This will be activated. This will be in inactive state. So you are getting the output from where to where? I naught to I3. Okay. When S2 equal to 1. Okay. So when S2 equal to 1, this becomes 0. This will be inactive state. This will be active state. So that means you are getting the input from where to where? I4 to I7. Either this or that. This is given to OR gate also. OR gate. Okay. Okay. Yeah. Next, you need to implement this what we call logic gates by using two cross one mux. Logic gates using two cross one mux. Logic gates using two cross one mux. First, first, what is the gate? Not gate, no? Not gate. Not gate. So this is the symbol for not gate. A y equal to what? A bar. Y equal to A bar. So how to design? Just to write the truth table. A and Y. 0 means 1. 1 means 0. Okay. So directly you can give it to here. Directly you can give it to this one selection line. This is A and this one is 1. Okay. And this is the output Y. Okay. This is given to 0. Okay. See here. When A equal to 0. which is connected. So directly you are giving these inputs to the here inputs. Okay. So if you see the Shannon's equation, y equal to what? A bar and 1 plus a and 0, no? Y equal to a bar. You got the expression for NOT gate. Mm. This is I0 and this is I1. Yeah, output. Yeah, we already seen the Boolean algebra. A and 0 equal to 0. So that means here A bar and 1 equal to A bar itself or 0. So this is you are getting A bar. Okay. Okay. Next. AND gate you see. AND gate. First you write the truth table. A, B, and output Y. Output Y. 0, 0, 0, 1, 1, 0, and 1, 1. You need to combine, you need to group 3 bits. As this is 0 means you need to consider A as selection line. Okay. And what is the truth table for AND gate? If any one of the input is low, the output is low. And both inputs are high, the output is high. Okay. And you see here, this is I naught. I naught equal to what? It is nowhere depending on B. 0. Okay. I1. Yeah, it is depending. Same as B, no? I can write B, no? 0 means 0, 1 means 1. I can write B, no? Okay. Yeah. So here, this is the. Mm, so I'm taking A as selection line. Here I'm giving to 0. Here I'm giving to input as B. So Y equal to what? A bar and 0 plus AB. So Y equal to 0 or AB. Y equal to AB. You got no? A bar and 0 plus AB. So A bar and 0 is 0 only. Y equal to AB plus 0 means AB. You are getting AB. Okay. Next. Um, OR gate using 2 cross 1 marks. First you write the truth table A, B, and the output is Y. 0, 0, 0, 1, 1, 0, 1, 1. You need to divide. If any one of the input is high, the output is high. Okay. And so this you need to consider as selection line. A you need to consider as selection line. And here I naught. I naught equal to what? Tell me. B. I1 equal to A. I1 equal to A. So now if you implement, mm, so input this is A and B and this is A. This is I naught and this is I1 and Y. So if you see the Shannon's equation, A bar B plus A and A. So Y equal to A and A equal to A plus or A bar B. So we in Boolean algebra we already seen absorption law, no? A or A bar B equal to what? B. A plus B. So Y equal to A plus B. You got no? Y equal to A plus B. Okay, na? Okay, shall I move forward? Okay, waiting for your response. Okay, yeah. Next, you try with this NAND gate and NOR gate. Tell me the inputs. First, you write the truth table. Okay. What is I naught? What you are getting? Mm, okay. Uh, uh, Output is any one of the input is low, the output is high. Okay. Output is high. Okay. Output is high, and this is a zero. Okay. Okay. You need to divide. This I not equal to what? One. I one equal to B bar. Now you can write I not equal to 1 and I one equal to B bar. Okay. So if you draw 2 cross 1 mux, 2 cross 1 mux. So here this is 1 and this is B bar. Y equal to A is the selection line. A bar and 1 plus A B bar. Y equal to, you can write as A bar plus B bar, no? From absorption law. If you apply De Morgan's law, this is equal to AB bar. NAND gate. NAND gate. You got NAND gate, no? NOR gate. Try for NOR gate. What is I naught? I naught equal to B bar. Okay. I1 equal to 0. Okay. So you got the mux, 2 cross 1 mux. I naught is B bar. I1 equal to 0. Y. Y equal to, selection line is A. A bar, B bar plus A and 0. So y equal to A bar B bar plus 0. Y equal to A bar B bar. Y equal to, if you apply De Morgan's law, A or B whole bar, same thing, NOR gate. XOR gate, I not equal to uh, B bar. Okay. Just 2 cross 1 mux. A, I naught B and I1 B bar and Y. Yeah, Shannon's equation A bar B plus AB bar y equal to AX or B. Okay, done. X nar. Okay, B bar B, selection line is A, 2 cross 1 mark. A bar B bar plus AB, y equal to AX nar B. Okay. Buffer, buffer, buffer. I not equal to. Means I need to implement this buffer by using 2 cross 1 marks. Inverter you already seen, no? Inverter we already see. Inverter seen, no? Same thing. One input has two inputs, no? Two inputs means, yeah, two input. No, one has one. 2 cross 1 marks. And A is the selection line. And y equal to A bar and 0 plus A and 1. Y equal to 0 or A. Y equal to A. Okay. So tomorrow we'll see how to implement this Boolean equations by using MUX. Okay. We'll see some examples how to implement this Boolean equations by using MUX. Meanwhile, you go through these concepts. Okay.